Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on satellite communication. For this video, I'm going to explain the three laws from Johannes Kepler. Okay, how does the satellite actually orbit around the Earth? There are actually three laws. I'm going to explain them one by one. So basically, this will be the objective of this video. This will be the part 4 series discussion on satellite communication. So guys, if you're keen to know more about satellite communication, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on satellite communication. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. This is very important to me because when more you guys actually help to press the like button, this video will have a better chances to reach up to a larger audience. So guys, give me a few seconds. Help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Before we come into the satellite orbit, so basically over here you can see that this is actually a solar system. How does the planet actually orbit around the sun is actually pretty much how does the satellites actually orbit around the Earth. So let's understand this a little bit more. So the orbital positions of spacecraft in a communication satellite system actually play a crucial role in determining the coverage and also the nature operation of the service that is actually provided. So all this I have discussed earlier on. The same law of motion that govern the movement of planet around the sun also apply to the artificial satellites that is orbiting the Earth. The satellite's orbit determination is actually based on the law of motion that is firstly developed by Johannes Kepler and then later on refined by Newton in 1665 using his own law of mechanisms and also the gravity law. So basically this gives you some idea, which means that the satellite orbit is pretty much the same. How does the planet actually orbit around the sun? There are actually two forces that is actually acting on the satellites. So basically this competing force that is actually act on the satellite will be the first one will be the gravity pull. So basically the gravity pull will actually pull the satellites towards the Earth. So we have this force is to pull the satellites towards the Earth, which we know this as gravity pull. Another force which is the orbital velocity. So this tends to pull it away from the Earth. So we have these two main forces. One, the gravity pull, which pull it towards the Earth. Another one, which is the orbital velocity, that they actually pull it away from the Earth. So basically the gravitational force, and the angular velocity force, they can be represented by these two equations. But this video, we are not going to dwell so much on these two equations. But we just want to know the nature of these two equations here. For example, this gravity force here, which is actually proportional to the satellite mass. This makes sense, right? Because how heavy the satellites will govern how much will be the gravity so-called pull. So the next one will be the angular velocity force. Again, you can see that it is actually proportional to the satellite velocity. And again, this makes sense because this is actually an angular velocity force, so it's actually related to the satellite velocity. Another term that I want to introduce will be the Kepler constant, which is governed by this equation here. So basically from here you can see that these are the two set of equations to compute the gravity force and also the angular velocity force. Okay, however, we note this, okay, we need to make this equivalent, okay, which means that the gravity force equals to the angular velocity force. We want to make it this two equal, which means that these two equations equal. And if we put this velocity on the left-hand side, we actually have this set of rules here. Okay, why we want to express the equation in this form here? Okay, so this result actually give us how much velocity that is actually required on the satellite so as to maintain the satellite at a constant orbit radius r away from the Earth. Okay, which means that if this satellite travel at a constant speed, it will maintain so-called a constant distance away from the Earth. Okay, so basically with this, we will be able to determine the nature of the service which we have studied earlier on. Next, okay, come into the wrong concept. Okay, so these are all the wrong concept. It's not a correct concept. I like to highlight it's a wrong concept that is actually happened many years ago. Okay, so basically these are all the early on wrong concept. Okay, initially everybody thought that the Earth will be at the center. Okay, all the planet actually rotate around the Earth. Okay, again, I like to so-called enforce this is wrong. Okay, so this is the wrong concept. Okay, so after that somebody refined. They said that the center is actually the sun and all the planet actually orbit around the sun. Again, all these are all the wrong concept. If you understand this Johannes Kepler law, okay, so these are all the wrong concept. Let's come to the Johannes Kepler first law. Okay, what is this first law? The Kepler first law as is applied to artificial satellites orbit. Okay, so actually this Kepler first law is actually applied to the solar system. Okay, however, this Kepler first law can also apply to this artificial satellites orbit. Okay, so can be simply stated as following. Okay, the path that is actually followed by a satellite around the Earth. Okay, so basically you can see that this path that is actually followed by a satellite around the Earth, okay, is actually an ellipse. Okay, you can see that the shape is actually ellipse here. Okay, with the center of mass of the Earth, okay, locate at one of the two foci for the ellipse. Okay, so basically the Earth here, okay, basically form one of the foci of the ellipse as in illustrate in this sentences here. So this is actually Kepler first law. Okay, so basically, imagine this: the satellite won't travel in a circle shape. It actually has a ellipse shape, and basically one of the foci will be the Earth. Okay, so if no other force that is actually act on the satellite, okay, whether is it intentionally through the orbit control or unintentional. Okay, for example, earlier on I did mention that we have this gravity force, okay, from other celestial body. Okay, the satellite will eventually settle into a elliptical orbit with the Earth at one of the foci of the ellipse. Okay, the size of the ellipse will actually depend on the satellite's mass and also the angular velocity, which I have explained earlier on. Okay, so basically this is the Kepler first law. Okay, let me quickly explain this so that you have a better idea on Kepler first law here. Okay, so Kepler first law is also known as the law of picker. Okay, so basically ellipse pickers laws here. Okay, so let's come to the illustration. What is this? You can see that I draw two ellipse here. Okay, so this is the first ellipse. This is another ellipse in green color here. Okay, so basically, how does this meaning here? Okay, and you can see that the foci is basically based on the sun. Okay, so basically, one of the foci point is actually the sun. Okay, so basically, on another foci point, this is actually the orbit path of planet one. So basically, planet one will turn in this structure here. So on another planet, basically again, the sun will be one of the foci position. Okay, so basically after that, there will be another foci position here. And you can see that planet 2 actually orbit in this direction. Okay, so all these are illustrated over here. So basically for solar system, okay, you actually has one of the foci point which is on the sun. And from here you realize that they don't turn in a circle shape. They actually so-called move in a ellipse shape, okay, as illustrated by this Kepler first law here. Next, okay, let's come into the Kepler second law. Okay, so Kepler second law can be simply stated as following. Okay, during equal time, okay, I will come to this. Okay, during equal time interval, a satellite cover equal area in its orbital plane. Okay, the shaded area A1, okay, so shaded area A1 represent the area that is covered by the satellite in an hour period near Earth. Okay, while the Kepler's second law actually state that any other 1 hour interval in the orbit will also cover an area that is equals to A1. Okay, so basically in short over here, okay, so basically this shaded area, okay, will be the same. For example, this is another area here, so will be the same. In short, okay, so basically this part here will take 1 hour to cover. Okay, since it is so-called nearer to the Earth, so basically you have a smaller region here. I will explain this a little bit more on the next slide. Okay, but when you are actually further away, okay, so which means that the area, okay, over here, okay, which is A2 will be equals to A1, okay, as illustrated over here. Don't worry, I will explain on the next slides. For example, okay, the area A2 that is swept up by the satellite in 1 hour at Apogee, okay, which is the furthest point from the Earth, is equals to A1, which I have illustrated here. So therefore, these two are equal. Okay, this result also show that the satellite's orbital velocity is not constant. Okay, so it moves faster near the Earth and slow down, okay, as it approach the Apogee. Okay, so basically imagine this, the satellites when they are actually very near to the Earth, they actually travel very fast. They actually travel very fast when they are actually near to the Earth. But once they are away from the Earth, they will be traveling very, very slow, which means that the velocity is not constant as is illustrated over here. So this is actually the Kepler's second law, okay, which means that the orbit velocity is not a constant velocity. Based on the location, when it is near to the Earth, it will travel at a faster velocity. When it is further away from the Earth, then it will start to travel very, very slower, so-called slower as compared when it is near to the Earth. Let's take in this so-called animation to understand this better. Okay, the orbit radius and the angular velocity of a planet in a elliptical orbit varies. Okay, so basically this is what I mentioned earlier on. The planet actually travel faster, okay, when it is closer to the sun, okay, and slower when it is further away from the sun. Okay, so this is the Kepler's second law that state that the blue sector has a constant area. Okay, so basically you can see that this is actually the solar system here. Okay, so basically you can see that this planet actually orbit. Okay, so basically you can see that they actually will be orbit faster. Okay, when they are actually closer to this foci point here. Okay, you can see that they actually move slower when they are further away from this foci point here. Okay, so basically this is what I have explained earlier on. Okay, the same blue area is swept up in a fixed time period. Okay, the green arrow actually represent the velocity. The purple arrow actually point it towards the sun, okay, which also represent the acceleration. The other two purple arrows are actually the component of acceleration, parallel and perpendicular to the velocity. Okay, so all these are not so important, but one I want to illustrate is basically when this planet, let's say this is a solar system, when it is near to the sun, it will actually travel faster. And when they are actually further away from the sun, you can see that they actually will travel slower. So this is actually Kepler's second law. Okay, so again, I like to so-called reiterate this Kepler's second law before I come into the third law here. So basically, Kepler's second law is also known as the law of equal area, okay, which I have explained earlier on. The shaded area A1, okay, which is a 1 hour time interval, let's say, okay, and A2, they are actually equal and they are actually swept up in equal time, okay, based on the planet one's orbit here. So basically, we have this planet one orbit here. So basically, you can see that the shaded region A1 is equals to A2. So this is actually Kepler's second law. Let's come to the Kepler third law. Okay, before I come into the Kepler third law, okay, so guys, again, if you have learned something from this video, please help me to like this video. And also, if you are new to this channel, please subscribe and turn on your notification bell. This is very important to me. Once again, I appreciate your strong support. Thank you so much. come to the Kepler third law. The square of the periodic time of orbit is actually proportional to the cube of the mean distance between the two bodies, okay, which is here. Okay, so this is actually the periodic time, okay, as illustrated here, which is the square. The square of the periodic time of the orbit, okay, is actually proportional to the cube. Okay, so basically this is the cube, okay, and then this is the mean distance between the two bodies, which is the Earth and the satellite for this case here. Okay, so basically this is the equation, and you can see that these are all the so-called the definition here, T, which is the orbit period. Okay, the A is actually the distance between the satellite and the Earth for this case here. Okay, and then we have this Kepler constant, which is the same number which I have introduced you earlier on. Okay, if the orbit is circular, okay, then A is equal to R, okay, because they are actually circular. And again, we are governed by this another equation here. Okay, this demonstrates that an very important result, okay, which means that this orbit radius, okay, which is a constant number multiplied by orbit period. Okay, so basically on my last few slides, I will explain this on the Kepler third law here. So under this condition, a specific orbit period is actually determined only by proper selection of the orbit radius. Okay, so this allowed the satellite's designer to select the orbit period that best meet the particular application that is required by locating the satellite at the proper orbit attitude here. Okay, so let's come to the quick understanding on this Kepler third law here. So basically, the Kepler third law is based on this equation here. Okay, for example, we have this R1, which is the distance away, okay, which is the distance away, the longest distance away, okay, from the sun, for example, here. And then we have this R2, which again will be the so-called the furthest away from the sun. So basically, these are the two planet, planet 1 and planet 2. Okay, so from this equation, you can see that this R1 cube, okay, which is this R1 cube, and if we take this R2 cube here, okay, basically they will be the same so-called the period. Okay, so this equation will be the same. They will be governed by a constant number. Okay, so basically this is actually the Kepler third law. Okay, so with this, I like to end my discussion. Okay, so in this discussion, I have explained on the three law of Kepler. Okay, so with this, I like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.